Hi, I'm Radu. I work at Vespa. And I wanted to start by asking who has heard of Vespa or worked with Vespa. Oh, wow, that's cool. What are Elasticsearch Solver? Cool. So I've been working for Vespa for about 1.5 years. I've worked with seen search engines for more than a decade. So if you have any questions in terms of like translating concepts from one to another. Okay, so this for those of you who haven't heard of Vespa, Vespa is kind of I just call it a search engine, but it's been doing both the vector side and the lexical side for a really long time. It's been open sourced in 2017, so it's fairly new to kind of the general public, but has a rather long history. And what I will focus on today is its support for tensors and how we can use tensors for various things. Namely, I'll first talk about dense vectors and different ways we can use them for search. And then I'll talk about sparse vectors and kind of wrap them up in terms of like how you can combine different signals in one ranking function. Yeah. I guess because there's just two of us instead of three, kind of last minute. I guess if you have any questions, you can also feel free to interrupt me, but to expand on what you're interested in. That being said, so I'll start with just like good old vector search. So the idea is you have an embedder model, you get text through it and it generates embeddings, right? So we can get text from the documents, and that will generate vectors, and then we can do the same with the query, and then we can check which documents are closer to query. We can do this going document by document, and that would be called brute force kind of approach. But most vector stores would also have a way to accelerate that. And Alessandro told me that there have been presentations here about HNSW, so I won't insist. If you're not familiar with HNSW, the way I think of it, at least, it's a bunch of sparsely connected graphs on top of each other. So you traverse the whole data structure kind of like a tree. So it scales better with data size than the brute force approach. What I would like to add is that not all HNSW implementations are the same. So in Vespa's case, we have one HNSW graph per field per node. That's not the case for all implementations. The idea is and this applies to all the data structures that scale kind of logarithmically with data. The idea is the fewer such data structures you have, the faster you're going to be. The challenge is how do you keep updating it? In the case of HNSW, you can always add to the graph, like you add a new data point, you connect it to whatever, to a bunch of other data points. It's a little bit more challenging to delete it because when you delete it, you'll have to also remove all the links to that node. Vespa would also repair the graph, so we'll create additional links around the node that would. So to some extent, the graph is sort of self-repairing, which has interesting implications because with HNSW, the order in which you insert data matters. Because when you add a new node, you're only aware of what's there. You have no idea what's coming after it. So you're going to create a bunch of links, and then so on and so forth. So because the graph is mutable, one cool side effect is that if the graph ended up weirdly just because of the coincidence of how data was introduced in the graph, as data churns, it might actually repair itself or get worse. Possible. The other thing is, with regards to not all HNSW implementations are equal, is you normally have a bunch of tunables in terms of, for example, the original HNSW. How many nodes do we look at when we insert a new node and stuff like that? But there are others as well, depending on the implementation. So a colleague of mine, his name is Andreas, he wrote a, what should I say, he coded UI for all those HNSW tunables, and I'll show you in a second. Before I would go there, because the number of tunables might be a bit, there's also an optimizer. So just put your data there, give your queries, and it can run them and suggest some values for those tunables. So so this is the thing. It's called HNSW parameter tuner, like that. So the idea is we have this graph which plots recall on this axis and latency in this axis. And because I only have 1 million documents, I'll just zoom in a little bit in terms of latency. So you can see I have 10 queries. Let me just add a few more. 100. This runs the queries real time, so I'll just add more threads. And you can see, because the queries are somewhat randomly generated, the recall is kind of all over the place. So one thing you can do to increase recall, and this is available in all of the HNSW implementations, both search engines, is like, okay, if you ask for like 10 vectors, you could explore more. So I can explore more than the vectors that I want to retrieve, and just retrieve the top end. So you can see like the latency tends to be a little higher, but the recall tends to be a bit higher as well. Another way to do this in Vespa is something called adaptive beam search. It's a paper that was written some time ago, and the point is it kind of tries to adaptively just look forward into the graph. And this seems to be a little bit more efficient than just retrieving a bunch of additional hits. Another thing that matters, so far we've just searched in the HNSW graph, but normal queries also have some filters. So if I would have a filter that is super selective, only match like a few documents, then actually searching in the HNSW graph is bad, because you're probably going to explore like the whole thing. And so you could have an approximate threshold, and Lucene has the same, where you just revert to brute force at some point. But on the other hand, if the filter is very broad, so it matches most of your data, then what might also help is to post filter, right? You just run it as if there was no filter, and then check which documents match, and you can overfetch. So again, these would be these tunables. When do we post filter, and how much do we overfetch to kind of compensate for the fact that we might be missing some of the documents. And the other thing, and Alessandro mentioned Acorn. This is a paper that was written about how you can, and again, there are other implementations as well, including Lucene. The idea is, instead of looking through the graph and checking if the node matches later, you can just kind of move forward, like ignoring hits that don't match your filter. So Vespa implements that as well, and there are some tunables around this area too. So I find this is not open sourced yet, just because it's kind of ugly, but we'll polish it and open source it as well. Okay. Questions so far? Okay, let me move on then. So this was assuming that you have one document, one vector per document, but you could have, let's say, one vector per chunk. So imagine you have Wikipedia pages, they can be about many things, and having one vector represent the whole page is not necessarily very precise. So because Vespa has tensors, it's quite trivial to just say, okay, I'm not going to have one vector per document, I'm going to have one vector per chunk. So I can add a chunk dimension to my vectors. Also create chunks in Vespa if I wanted to, but normally you do it in the pipeline. And then you can search for documents that have, let's say I want top 100 documents. I can search for top 100 documents that contain chunks that are relevant to my query. But then the way I rank documents can be different. I can say, I can rank them through a combination of signals, and I'll show some examples later on. You could, for example, say not only, you can say the maximum chunk, the most relevant chunk, gives the relevance of the document, or the top 3, or all of them, or some sort of combination. The other thing I'd like to bring up is when we have multiple vectors, not only for the document, but also for the query. And I'm pretty sure some of you are familiar with Colbert. The idea here is we can have one vector per word, and we can go through every word of the query and check what are the words in the document that match best, and add those up, and that will be the total score. The thing that I find cooler about this idea of late instruction is it also works with images. So there are models like Colpali, which can take an image, and you can have one embedding per patch of the image. So it divides the image in a bunch of patches. And this seems to work really well in practice. And you could, for example, by the way, I did not mention this. I will share the slides at the end, so there'll be a QR code with all the slides. And I have lots of links here to kind of expand on these topics. So you can take PDFs, and you can just basically take each image as a page, each page as an image, and then get that through Colpali, and it will generate embeddings. And these embeddings will live in the same vector space as the query, right? You can go get the query through the same. And you can actually ask questions of your images. And I have a short demo here to show, except that this got in the way, this Zoom. Again, I'm technology challenged. There you go. Okay. So this is, again, open source. The whole thing is in Hugging Face, and I'll just run one query, my favorite one, child jumps over a puddle, and it actually finds a child jumping over. I'm not sure if it's shown here, but often it actually can also highlight the patches that match. So that's the thing about both Colbert and Colpali. You can highlight the parts of the document that match your query best. Okay, so this was dense vectors. And the thing with dense vectors is dimensions are implicit, right? Like we don't know exactly what the first dimension is, or the third, or whatever. Sometimes it's useful to have explicit dimensions. The example I'll go through with is second-hand car search. And some of you have been to Haystack and probably seen this demo. The idea is cars have different attributes, like price, miles per gallon, age. And we can extract those features, and we can put them in a sparse tensor. So for example, here I have a Ford Focus with a manual transmission, with a really good price. So generally, the idea is to kind of normalize these values. And so a higher price value means a good price, and IMPG, and then, age, and so on. And what we can do is we can take preferences with regards to these features from users. We can either get them implicitly or ask for them, and then we create a sparse tensor for the query. So for example, let's say this user cares about the car to be new and should have few miles on it, and to a lesser extent about some of the brands that this user likes. And then what we can do is we can do a dot product between the sparse tensor with user preferences and the sparse tensor of the secondhand cars. And then this will give us an aggregate score of how well the car matches my preferences. So I have a demo for that as well. The idea behind this is when I'm searching, let's say for a secondhand car, I have some criteria that are non-negotiable, right? Like let's say I cannot drive, I don't have a driving license to drive a manual. So I will have to search for an automatic, right? So this is a hard criteria, but most of the criteria I use when I search for something, let's say in e-commerce, are just softer and sometimes conflicting, right? So let's say I want a cheap and reliable car. I'm just going to say this here. I want a cheap and reliable car. The LLMs are slow, so I can talk while this is crunching. So these are kind of conflicting, right? If I would just filter by price, I might not see cars that are reliable. If I just filter by, I don't know, some brands and other things, I might see just only expensive cars. Plus, I don't know maybe what reliable means. You know, are there some brands that are more reliable? You know, does mileage matter more than age or the other way around? Here, the assumption was that maybe LLMs know a little bit better than someone that doesn't know at all. So that's hence the implementation here of I want a cheap and reliable car, and it automatically thought that, okay, you probably want a Toyota or a Honda, or you care about mileage more than something else and price. And I created a sparse tensor for me, and then this does the dot product, and I can adjust these. I can keep talking to the LLM, or I can manually adjust the sliders. Yeah, that's the gist of the idea. And you don't have to have one or the other. You can combine these things in different expressions. And again, this is not unique to Vespa, but maybe the way to express this is. So this is an example of taking that dot product, but also adding in the mix, for example, where the car is located, distance from me. Okay. So generally, attributes of documents can be ratings, can be, I don't know how popular a product is. And again, the idea here would be to normalize. So here's an example where we also take the BM25 lexical score. With BM25 scores can be a bit all over the place, can be very high and kind of dominate your score, very low and become insignificant. So we can normalize this with an expression like an arctangent, and then we can also add a weight. I mean, we can add weights anywhere, and then combine that with sparse or vector scores or both. And those signals, which don't have to be, let's say for lexical search, it doesn't have to be the actual BM25 score. It can be only the term frequency. It can be distance between words. Whatever attributes we think are relevant, we can take them and make a formula with those, or we can just give them as features to a model. Like could be a GBM model, could be on an X model, and we can make the model come up with the weights. And if the model is expensive, of course, the search will get slow, which is where we can use the model as a re-ranker. We don't have to use the model for all the results, even though we could. And in Vespa, there are two ways to do re-ranking. One is to do it on the actual nodes that are running the query. And yeah, let's say they take the top 10,000 documents and re-rank them using this model, or you can do this on the stateless layer where the results are merged, and that's where you can have an even more expensive model that has all the hits that surfaced, and can also run the model on the GPU. So yeah, what I would suggest, especially as a generic approach with Vespa, probably this works for search engines, is like to think about which dimensions matter, normalize them, and combine them. With Vespa, I would use tensor math wherever possible because that's the fastest way. Like if the way I showed earlier with the dot product, this would be much faster than if in a rank profile, I would just say, okay, multiply miles per gallon with miles per gallon here and add this up, and then it would be just much slower. But you can use the rank profile as kind of a glue, different signals and combinations. Yeah, and if the model is more expensive, you would use it as a re-rank. But I guess Sandra will talk a lot more about this. Yeah, how to generate judgments, to train models, stuff like that. As promised, the slides you can have here, and there are links to, I think, all those demos, minus the HNSW tuner, which is not yet available, but when it will be, we'll sure to tweet about it. You can pick me on LinkedIn, you can pick me on Vespa Slack.